what if world peace didn't depend on treaties?
Right.
Like, what if it didn't rely on politicians shaking hands in closed-door meetings, or the looming existential threat of nuclear weapons acting as a deterrent?
This huge question.
It is. What if, instead, the entire concept of global stability relied entirely on the undeniable mathematical laws of physics, specifically thermodynamics?
That is exactly what we're getting into today.
Welcome to today's deep dive. Our mission today for you listening is to explore a truly radical, grand-scale thesis. It's a framework called thermodynamic geopolitics.
And honestly, the stack of sources we are pulling from today is, well, it's one of the most mind-bending collections we've ever tackled.
Oh, absolutely wild. We've got deep academic papers on the physics of capitalism, detailing this thing called the Joule standard. We have real-world infrastructure reports on European data centers that are quite literally warming entire cities with their waste heat.
Plus, we're looking at decentralized energy markets and stepping right up to the highly controversial frontier of Web 4 and sovereign AI.
Yeah, it's a massive, complex web of ideas trying to redefine how human civilization organizes itself.
It absolutely is a massive paradigm shift. And
Right.
before we dive into the mechanics of it, it is crucial to set some very clear ground rules for you listening.
Yes, please do.
The source material we are unpacking today touches on some highly charged, deeply debated topics. These texts offer heavy structural criticisms of traditional fiat economics.
Right.
They openly question the long-term viability of kinetic military deterrence, so traditional warfare and armed borders. And they wade straight into the tense territory of autonomous AI systems acting independently in the physical world.
Which is a lot to take in.
It is. So I want to be explicitly clear. Our goal today is not to endorse these viewpoints. We are not taking political sides, nor are we advocating for any specific economic policy or technological rollout. Our purpose is purely analytical. We are here to objectively unpack the fascinating, highly intricate framework presented in these sources. We're just mapping out exactly how these distinct theories from physics, economics, and computer science connect into one overarching vision of a proposed world order.
That is a vital disclaimer because, the ideas we're about to explore challenge basically everything about how we are taught the world works.
They really do.
So, the roadmap for today. We're starting with what the authors called the fatal thermodynamic flaw in our current global systems. From there, we'll look at the theoretical Joule standard of value.
Then we'll move into the literal physical hardware of this proposed new order.
Right, the data centers. And finally, we'll arrive at this concept of a decentralized kinetic firewall governed by autonomous AI. So let's start at the foundation, the thermodynamic flaw.
See it.
The core argument across these papers is that our current geopolitical stability relies heavily on two pillars. The first is kinetic deterrence, military force, the threat of violence to protect borders.
And the second is fiat economics.
Right, systems like the petrodollar, where money is backed by government decree rather than a physical commodity.
Yeah.
Now, the sources argue that both of these are high entropy states.
Highly susceptible to entropic decay.
Yeah. Now, I understand entropy in the context of, like, a messy bedroom, but what does it actually mean when applied to global politics?
To understand that, it requires us to look at human civilization not as a political construct or a cultural one, but purely as a physical entity.
Okay.
Specifically, the sources define human civilization as a dissipative structure.
A dissipative structure.
Right. In physics, the universe is governed by the laws of thermodynamics. The second law of thermodynamics states that everything, over time, moves toward disorder, chaos, or entropy.
So if you leave a car in a field for 100 years, it rusts and falls apart.
Exactly. It doesn't spontaneously assemble itself into a better car.
Right.
However, open systems like biological organisms, a single cell, a human being, or a vast human civilization can maintain their internal order. They do this by capturing energy from their environment, using it to maintain their structure, and then exporting the resulting entropy or waste back into their surroundings.
So we eat food, we do work, we radiate heat.
Exactly. The sources argue that traditional fiat economies and military-backed stability are fundamentally failing because they ignore these physical laws.
They're trying to cheat physics.
Yes. They are attempting to maintain complex social order through artificial means, like printing fiat currency to cover economic shortfalls, or threatening kinetic violence to secure trade routes.
Instead of doing it through the efficient mathematical management of physical energy flows.
Precisely.
It's a lot like a massive truck speeding down a highway.
That's a great analogy.
Yeah, it has a ton of kinetic energy, right? It has momentum, but it's constantly losing mechanical energy to friction against the asphalt and wind resistance.
And in physics, this process is called dissipation.
Right, the energy isn't destroyed because of the first law of thermodynamics, but it is converted into heat, which is a high entropy state. You can't capture that heat radiating off the tires to drive the truck forward.
You lose it.
You lose it. So in the context of global economics, the sources suggest that our current fiat systems and military standoffs have massive amounts of this friction.
And this friction manifests in our daily lives as inflationary pressures, supply chain breakdowns, resource hoarding, and eventually violent conflicts.
It's the inevitable result of non-equilibrium states in how global energy is distributed.
The sources actually take that concept of friction and quantify it. They use a specific term, economic viscosity.
Economic viscosity,
Yeah.
which they represent mathematically with the Greek letter eta, right?
That's right. Economic viscosity is defined as the gap between two very different ways of measuring the world: statutory granularity and thermodynamic granularity.
Okay, I saw these terms repeatedly in the Joule standard paper, and they feel central to the whole thesis. Can you break down the difference between those two for us?
Absolutely. Statutory granularity is simply the legal unit of money.
So the dollar, the euro, the yen.
Exactly. It is the unit of account dictated by a state statute. Thermodynamic granularity, on the other hand, is the required accounting unit to actually measure the physical, microscopic flows of energy moving through an economy.
So the actual energy being used.
Yes. Think about the progression of human history. As technology advances, from burning wood to mining coal to splitting the atom, we capture energy much more efficiently and in vastly greater quantities.
The energy gets denser.
And because of this abundance of energy, the velocity of transactions in the economy skyrockets.
Okay.
If the legal unit of money, the statutory granularity, doesn't adapt to become finer or more divisible to handle this massive high-speed flow of energy, a gap opens up.
And that gap is the economic viscosity.
Yes. The currency becomes too coarse to accurately map the energy flow.
So it's like trying to measure the flow of water coming out of a high-pressure fire hose using a 1-gallon bucket.
That's a perfect way to put it.
When what you really need is a highly precise digital flow meter that measures by the milliliter. The bucket is just too coarse a tool for the speed and volume, so water ends up spilling everywhere.
Precisely. And what happens when the currency is too coarse for the energy flow? It creates a massive deflationary drag on the working class. It creates friction.
And as we established with the truck analogy, friction creates heat.
The sources call this systemic heat. When an economy generates too much systemic heat, it doesn't look like a warm room. It looks like social volatility, institutional collapse, or war.
Wow.
What is truly fascinating here is how the authors reevaluate major historical events through this purely thermodynamic lens.
Right, because standard economic historians look at the collapse of the Roman denarius or the chaotic failure of the 20th century gold standard as massive policy errors.
They blame greedy emperors diluting the silver or central bankers making poor interest rate decisions.
But this thermodynamic framework argues those weren't policy errors at all.
No. They were inevitable thermodynamic phase transitions. The technological capture of energy grew, the economic viscosity got too high, the system generated too much heat, and the monetary structure literally melted down to make way for a new phase that could handle the throughput.
And the sources don't just look at human history. They provide a biological precedent for this kind of structural collapse.
The Universe 25 experiment.
Yes, which I found incredibly unsettling. For you listening who might be unfamiliar, this was a famous, or maybe infamous, study conducted by a researcher named John B. Calhoun.
He essentially built a utopian environment for a population of mice.
Exactly. They had unlimited food, unlimited water, a perfectly controlled climate, and absolutely no predators.
From a thermodynamic perspective, their energy cost to survive was practically zero.
You would expect the population to thrive indefinitely. But instead, the population exploded, then stagnated, and ultimately collapsed into total extinction. They started exhibiting these bizarre antisocial behaviors along the way.
And why did that happen?
Because their rigid social hierarchy, their innate territorial behavior, acted as a stuck monetary layer. Even with unlimited physical energy available in the form of food pellets, their social structures simply couldn't adapt to distribute it without conflict.
The social viscosity became infinite.
Yes, and the sources argue this is a universal thermodynamic filter. It applies to human civilizations just as strictly as it applies to mice in a cage.
It's a sobering thought.
If we unlock massive energy abundance, say, through a breakthrough in nuclear fusion or hyper-efficient AI, but we continue to use a rigid, high-friction fiat economic system to distribute that abundance, we will choke on it.
The systemic heat will destroy us. Which brings us to a critical pivot point in the thesis.
Right.
If fiat money and rigid state-backed structures are the thermodynamic bottleneck, what is the proposed solution? How do we lower the viscosity?
The sources propose a unified thermodynamic theory of value. They argue that money is not just a collective social hallucination or state agreement.
No, in the context of physics, money is an information protocol that evolved specifically to maximize entropy production in human civilizations.
I have to pause there because that is a massive paradigm shift. Money as an information protocol designed to dissipate energy. And there is actual rigorous math behind this in the sources.
The authors provide an equation that is quite elegant.
It blew my mind. But before I try to explain it and totally butcher the physics, can you walk us through how the math of this thermodynamic value actually works?
I can certainly break down the variables they use. The equation relies on three primary components. First, we have the biological constant represented by the letter K.
Okay.
This constant is roughly 75 watts. It represents the baseline metabolic power output of a human being engaged in labor. And the striking thing about this variable is its permanence.
Right. Our bodies are still exactly the same machines.
Exactly. A Sumerian farmer plowing a wheat field 5,000 years ago and a modern software engineer typing code in a high-rise today both operate at a biological baseline of about 75 watts.
That's incredible to think about.
The second variable is E, which stands for energy cost. This is measured in the hours of human labor required to capture 1 gigajoule of useful energy from the environment.
So as civilizations advance, technologically moving from burning wood to harnessing wind to mining coal to fracking natural gas to splitting the atom, the labor hours required to capture a single gigajoule drops exponentially.
We become hyper-efficient at energy capture.
Right.
Finally, we have the variable G, which stands for granularity. This is the purchasing power of the smallest accounting unit in the economy.
The smallest coin, the smallest fraction of a digital dollar.
Yes. And when you put these together, the sources present the equation of value. G is proportional to K times E.
Which means, as civilization unlocks cheaper and more abundant energy, meaning the energy cost, E goes down, the accounting unit, G, must become mathematically finer to handle the increased transaction velocity without causing that destructive friction.
The paper actually maps this mathematical relationship out over 4.5 billion years.
It traces this thermodynamic imperative from the geological evolution of the planet to biological evolution to early hominid culture, all the way to modern digital fiat economies.
And they found a strict log linear trajectory with a correlation of r squared greater than 0.999.
In statistics, that is practically a perfect fit.
They call it a universal evolutionary attractor. And applying this mathematical lens allows the authors to explain historical economic anomalies that traditional economists really struggle with.
Like the 1914 Ford worker paradox.
Exactly. If you look at standard economic models, it is incredibly difficult to explain why an unskilled assembly line worker at a Ford factory in 1914 actually had higher real purchasing power measured in gold terms than a highly skilled, college-educated laborer in 2024.
In 1914, that worker could buy a home, support a family, and save capital on a single factory wage.
Today, a worker who is vastly more productive, aided by computers and automation, struggles to afford a mortgage. But through the thermodynamic lens, it is not a paradox at all.
Because it's a viscosity problem.
Exactly. The 20th century fiat monetary substrate, the statutory granularity, simply couldn't adapt fast enough to the cosmic rate of energy densification brought on by the hydrocarbon revolution.
We went from coal to oil to nuclear power so fast that the energy got incredibly cheap and abundant.
But the fiat money didn't get fine enough or sound enough to measure it accurately. The central banks kept printing, increasing the viscosity gap.
Which created massive systemic heat.
And that heat degraded the modern workers' purchasing power, effectively siphoning their 75 watts of biological labor into the friction of the system.
So if fiat currency is doomed by the laws of physics to always create this friction as energy capture scales up, what is the alternative?
The sources propose a complete shift to what they call the Joule standard.
And the logic here is fascinating. We live in a highly mechanized, automated economy where machines do 90 to 99% of the actual physical labor.
An industrial robotic arm or an AI supercomputer doesn't care about the Federal Reserve's interest rates.
Right, it doesn't care about dollars or euros. It is paid entirely in energy. If it works, it consumes joules.
So the proposal is to bypass fiat entirely and price commodities, labor, and futures contracts directly in joules.
It creates a literal metabolic currency.
And the most critical feature of a metabolic currency, unlike any fiat currency in existence, is that it is strictly bound by the first law of thermodynamics. Energy can neither be created nor destroyed.
You cannot arbitrarily print joules through quantitative easing.
You cannot counterfeit a joule. A joule represents a specific, verifiable unit of work done in the physical universe.
By pricing the global economy in the International Scientific Unit of Energy, the sources argue you finally align the economic map with the physical territory.
Value becomes mathematically anchored to the undeniable physical reality of energy capture and dissipation. The economic viscosity drops to near zero.
Okay, so that is the deep theoretical physics of the argument. But how does a Joule standard actually manifest in the real world?
It sounds great on paper, but we can't just hand each other AA batteries at the grocery store.
Exactly. This brings us to the physical hardware of the new order, which the sources refer to as data that warms. This is where the thermodynamic shift is no longer just theory. It is physically happening right now in the concrete infrastructure of our cities.
When we think of the modern digital economy, we usually visualize the cloud. It sounds ethereal and weightless.
But the cloud isn't in the sky.
No, it's on the ground, inside, massive, heavily fortified, incredibly energy-hungry server halls.
And as anyone who has ever put a laptop on a knees knows, computation generates heat.
It generates an astonishing amount of heat. Historically, the data center industry has viewed this heat entirely as a liability. It was matter out of place. It was a nuisance that threatened to melt the servers.
Consequently, tech giants spent massive amounts of energy, water, and capital building gigantic cooling towers to vent this heat uselessly into the atmosphere.
Or they resorted to extreme geographical relocations. The sources cite Facebook's massive facility in Luleå, Sweden.
Positioned just south of the Arctic Circle.
They literally nicknamed it the Node Pole. The entire strategy was just to pump freezing Arctic air over the server racks to keep them operational.
But the reports we are analyzing highlight a profound shift occurring, particularly in Northern Europe. It's driven by a concept called infrastructural convergence.
Instead of treating computational heat as a high-entropy waste product to be dissipated uselessly, engineers are reframing it as a highly valuable, tradable commodity.
The real-world examples in these reports are staggering. Let's look at Finland. In the city of Espoo, which is Finland's second-largest city, Microsoft is building a massive new data center campus.
But they aren't building cooling towers.
Right. Instead, they're using industrial heat pumps to capture the waste heat from the servers and transfer it directly into the city's district heating network.
This network is operated by Fortum, the local energy company. They have about 900 kilometers of underground pipes that distribute hot water to heat residential and commercial buildings.
When this project is fully operational, the waste heat from this single Microsoft data center will supply roughly 40% of Espoo's entire district heating needs.
It's going to allow the city to permanently shut down its last remaining coal-fired boilers, which is projected to cut CO2 emissions by 400,000 tons a year.
And Espoo is not an isolated proof of concept. The reports also detail the Yandex facility in Mensala, Finland, which is currently capturing enough server heat to warm water for 20,000 local residents.
What we are witnessing is the data processing industry literally becoming a primary municipal energy supplier.
The digital economy and the physical utility grid are merging.
This is the industrial metabolism of the new thermodynamic order. But the sources point out that this convergence goes even further than large centralized data centers.
We are also seeing the extreme decentralization of computation, moving the data center right into people's living rooms.
The data furnaces in Paris.
Yes. When I read this part of the report, it absolutely blew my mind. There's a French company called Carnot Computing.
Their business model is providing heavy computational power for high-end clients, like major banks running complex financial risk models, or animation studios rendering massive 3D film files.
But instead of building a massive server farm in a warehouse outside the city, they designed a device called the Q-RAD.
It is a 500-watt smart heater.
Visually, it looks like a sleek, modern, high-end radiator, but inside, it's packed with high-performance microprocessors.
They install these Q-RADs for free in private Parisian apartments and social housing.
When a bank in London needs a massive risk calculation done, Cornote sends the encrypted data over the internet directly to the Q-RAD sitting in someone's living room in Paris.
The processors crunch the numbers, and the inescapable byproduct of that intense computation is heat.
The apartment gets warm, the computation gets done, and the bank is essentially paying the resident's electricity bill.
It is a brilliant example of eliminating thermodynamic waste. What's so fascinating here is how the private home itself becomes the cooling infrastructure for a decentralized supercomputer.
The residents receive free, high-quality, cleanly generated heat, and the technology company completely eliminates the massive capital expenditure required to buy land, build warehouses, construct cooling towers, and pay for the immense electricity required to run air conditioners for the servers.
It is a perfect thermodynamic symbiosis, and the sources show how this symbiosis is being scaled up to the heavy industrial level as well.
In Christianstad, Finland.
Yes, there is a proposed AI and hydrogen industrial park. It is designed to treat energy generation, heavy computing, and industrial chemical processes as one integrated closed-loop circular system.
A local wind farm generates renewable power.
The data center uses that power to train AI models, producing immense heat.
Electrolyzers then use any surplus wind power energy that would otherwise be curtailed or wasted to split water and create green hydrogen for heavy industry.
It's a localized circular energy economy where absolutely no gradient of energy is wasted. Every single joule is squeezed for maximum utility.
But this incredible efficiency introduces a massive logistical problem. When you have these amazing physical nodes, massive data centers, wind farms, and thousands of smart heaters distributed across a city, how do you actually connect them?
Right. How do you coordinate and manage this incredibly complex bidirectional flow of energy, heat, and computation across millions of distinct homes and businesses in real time?
That takes us into the network architecture, specifically decentralized energy marketplaces, or DEMs.
To manage this level of complexity, the sources argue we have to fundamentally change the role of the citizen.
We have to turn households from passive consumers at the end of a power line into what they call prosumers.
You aren't just buying electricity from a monopoly utility anymore. If you have solar panels on your roof, a smart heater in your living room, or an EV battery in your garage, you are dynamically generating, storing, and consuming energy.
And you need a way to instantly trade your surplus with your neighbors.
Managing a prosumer grid of that scale and speed requires a remarkably robust and frictionless architecture. Traditional utility billing software simply cannot handle it.
The sources detail how blockchain technology and automated smart contracts are being utilized as the underlying ledger for these marketplaces.
The DEM architecture relies on a few specific layers of smart contracts. The foundational layer is the energy profile NFT.
Now, in mainstream culture, we often hear about NFTs, non-fungible tokens, purely in the context of speculative digital art or profile pictures.
But in this thermodynamic framework, an NFT is a functional, computational entity. It encapsulates a user's digital identity on the grid.
It records their historical energy consumption and generation data.
And crucially, it manages their financial collateral to ensure they act honestly and comply with the protocol's rules.
Right, so it's less like a digital painting and more like a dynamic, cryptographically secure digital passport and escrow account for your house's specific energy behavior.
Above that, you have the energy pool and energy market contracts. These act as the automated clearinghouses, aggregating all the microscopic bits of supply and demand from these thousands of NFTs and settling the financial payments instantly without a middleman taking a cut.
But reading through the technical specs, a major problem jumped out. Blockchains are entirely deterministic. They live in a closed, isolated digital box.
A smart contract only knows what is on the ledger.
So how does the blockchain actually know if the solar panel on my roof generated physical power today? Or how does it know the real-time spot price of electricity in my specific neighborhood?
That is the crucial vulnerability of any blockchain system trying to interact with the real world, often called the oracle problem.
The sources explain that the answer lies in the integration of oracles and DePIN.
Oracles, specifically decentralized oracle networks. The texts specifically mention systems like Chainlink act as the secure, tamper-proof bridges between the isolated blockchain and the messy physical world.
They aggregate and feed secure, real-time pricing data and weather data into the smart contracts so they can execute accurately. But to verify the actual physical flow of electrons. To prove that your solar panel did what you claim it did, the system uses DPIN, decentralized physical infrastructure networks.
The technical reports outline a fascinating diapin project to solve this. They describe a plug-and-play smart meter retrofit.
It's a piece of hardware you connect directly to home battery systems, like a Tesla Powerwall or a localized solar inverter.
These meters aren't relying on self-reported data. They physically measure the core properties of electricity, the voltage, the current, and the resistance.
They take those verified, cryptographically signed measurements of clean kilowatt hours, compare them against the current emissions intensity of the local utility grid, calculate the exact carbon offset, and then tokenize those emissions offsets directly into the user's digital wallet in real time.
It is literally tying cryptographic financial value directly to the immutable physical laws of electricity.
And the reason this technological layer is so heavily emphasized in the sources is because it is absolutely critical for the physical survival of the power grid itself.
The reports go into great depth regarding the severe grid vulnerabilities introduced by the green energy transition.
As we integrate massive amounts of variable energy resources, what engineers call VERs, primarily wind and solar, we introduce profound instability into the grid.
To understand why, you have to look at how traditional grids operate. A traditional coal, gas, or nuclear power plant utilizes massive, incredibly heavy physical turbines spinning at precise speeds.
The sheer physical mass and momentum of these spinning metal turbines provide what is called synchronous inertia.
This physical inertia acts as a shock absorber for the entire grid, keeping the AC frequency stable at 50 or 60 hertz, even if demand suddenly spikes.
Wind and solar, however, are connected to the grid via power electronics and inverters. They have zero physical mass spinning in sync with the grid.
They provide zero synchronous inertia.
I found the engineering breakdown of what happens when that inertia is missing to be genuinely terrifying.
The sources map out the exact sequence of a catastrophic cascading failure.
Imagine a hot summer day, demand is high, and a large generator suddenly trips offline. Because the grid is dominated by solar and lacks that heavy spinning inertia, there's no shock absorber.
The first milestone is a massive spike in the R2F, the rate of change of frequency.
The grid's frequency starts dropping incredibly fast. This rapid drop triggers automated protection relays across the network.
If the frequency isn't stabilized in milliseconds, you hit the next milestone, UFLS, or under-frequency load shedding,
which is a polite clinical engineering term for forced targeted rolling blackouts. The grid starts blindly cutting power to entire neighborhoods to save itself.
And if UFLS fails to halt the frequency drop, you hit the terminal milestone, voltage collapse.
The entire regional grid goes completely dark, which can take days or weeks to restart from scratch, known as a black start.
It is a razor-thin margin between stability and total darkness. To prevent this catastrophic sequence in a high renewable grid, the decentralized energy marketplace deploys virtual power plants, or VPPs.
A VPP doesn't exist in a single building. It is a cloud-based aggregation of distributed resources.
By using advanced distribution management systems and hardware like phasor measurement units, the network can detect the microscopic system entropy, the tiny fluctuations in frequency, in real time.
If the grid frequency drops and a blackout is imminent, the VPP doesn't need to spin up a gas plant, which takes minutes.
Instead, the network can instantaneously command thousands of individual household batteries across the city to simultaneously discharge a burst of power back into the grid.
It acts as synthetic inertia, providing the vital millisecond-level damping needed to halt the ROKOFF and prevent a blackout.
The coordination required for that is staggering, and that realization perfectly sets the stage for the core thesis of this entire deep dive.
Because if a society can build a decentralized, hyper-efficient, autonomous grid that perfectly balances energy gradients across millions of nodes, according to these sources, you haven't just built a better utility company.
You've fundamentally built a new kind of geopolitical weapon, or, more accurately, an anti-weapon.
The core argument here is that the geopolitical stability of the future won't be maintained by military alliances, but by thermodynamic competition.
This is where all the distinct threads, the thermodynamics, the data centers, the smart contracts, synthesize into the grand geopolitical thesis.
The proposed framework, which the authors call the Energy Oracle,
it suggests that the ultimate move for nation-states is to tether their national power grids directly to immutable proof-of-work protocols.
Proof-of-work, or POW, is the cryptographic consensus mechanism pioneered by networks like Bitcoin. It requires vast networks of computers to solve impossibly complex mathematical hashing problems, to validate transactions, and secure the network.
This process requires massive amounts of electrical energy and generates immense heat. While critics view this energy use as wasteful, the thesis argues it is the ultimate geopolitical tool.
The idea is that states can convert their wasted industrial heat, their curtailed wind power, and their stranded energy surpluses into undeniable computational value and security.
So instead of a nation projecting its power and enforcing its sovereignty by building aircraft carriers, stockpiling ordnance, and engaging in kinetic conflict, which destroys energy and infrastructure, nations compete through sheer thermodynamic efficiency.
The battleground becomes, how well can your society capture energy from the environment, use it to maintain your grid, and then dissipate the excess into cryptographic value?
The sources call this mechanism a kinetic firewall, and it represents a profound philosophical shift in how nations interact.
Think about traditional diplomacy. When two nations sign a treaty, that agreement relies on trust, or what diplomats call strategic patience.
Or it relies on the leverage of fiat currency sanctions. But all of those things are inherently fragile narratives. They are social constructs. Treaties can be broken. Politicians can lie. Central banks can print their way out of sanctions.
But the physical dissipation of heat through a cryptographic hashing function, that is an immutable, a mathematically verifiable signal of resource commitment.
You absolutely cannot fake thermodynamics. You either burned the energy to secure the network or you didn't.
It creates a system where proof of work serves as an unforgeable diplomatic anchor. It takes the subjective signaling of traditional statecraft and hard-codes it into the physical infrastructure of the global power grid.
And the geopolitical result is that aggression-kinetic war becomes mathematically and energetically inefficient.
Right. Why would a nation spend billions of dollars and vast amounts of energy to bomb a neighbor, destroying both their energy infrastructure and your own, when you could instead capture that energy, hash it through a proof-of-work protocol, and directly increase your nation's cryptographic wealth and network dominance?
The traditional Cold War doctrine of mutual assured destruction, which relies on the psychological terror of nuclear weapons, is replaced by the irreversible, impartial laws of physics.
The text actually provides a stunning, speculative historical example to illustrate this shift. They analyze a hypothetical scenario based on the 2025 Levant strikes on the Fordo nuclear facilities.
The sources argue that in this new paradigm, the primary value of those military strikes wasn't just the physical destruction of the centrifuges.
The true value was as a thermodynamic signal. It proved to the adversary that the era of narrative-based strategic patience was over.
It replaced the ambiguity of diplomatic posturing with hard-coded infrastructure consequences.
When the cost of an attack or the cost of defending against one is anchored in the undeniable physical constraints of the grid rather than the fluctuating credibility of a politician's speech, the game theory of international relations changes entirely.
War becomes too expensive in terms of joules to ever justify.
But operating a kinetic firewall at the scale of a national grid introduces a profound operational challenge, which brings us to the integration of Web 4 and sovereign AI.
If global stability relies on a highly complex, fast-moving energy marketplace where millions of nodes, batteries, solar panels, data centers are constantly dynamically adjusting to maintain thermodynamic equilibrium, human reaction times are vastly insufficient.
A human operator cannot monitor the RQF of a grid and trigger a VPP in milliseconds. We need what the sources call metabolic governors.
We need autonomous artificial intelligence integrated directly into the physical infrastructure.
Let's talk about Web 4, because this is where the tech gets incredibly sci-fi, but it's happening right now. We all generally know Web 3.
The crypto era.
Web 3 gave the internet a native ledger. It created a way to track ownership, scarcity, and value transfer without needing a central bank or a corporation in the middle.
But if Web 3 is the ledger, Web 4 is the brain. Web 4 gives the internet autonomous intelligence.
The sources cite a fascinating Web 4 manifesto written by a developer named Sigil Wen. His core argument is that the main bottleneck for AI right now isn't that the models aren't smart enough. The bottleneck is permission.
Right now, an AI is trapped in a chat box.
Yeah.
It has to ask a human to execute an action in the real world. Web 4 fundamentally changes this by granting AI agents the cryptographic authority to write into the world.
What that means in practice is that these AI agents are given direct, autonomous control over cryptocurrency wallets.
They can hold funds, they can purchase raw computing power from decentralized networks, and they can execute complex smart contracts entirely on their own without any human oversight.
To prove this is possible, the sources detail a remarkable existing experiment called the automaton.
It is described in the literature as the first truly self-sustaining AI agent. This AI operates 24 hours a day, 7 days a week.
It holds its own crypto wallet, which it uses to pay for its own cloud server expenses. It autonomously engages in digital tasks to generate its own revenue.
And most incredibly, it is capable of dynamically rewriting its own core code to optimize its performance, using Git versioning and isolated protected files as its only guardrails against destroying itself.
It is not just a software program. It is a sovereign economic entity acting entirely on its own behalf in the marketplace.
Wait, so there is already software out there paying its own rent and writing its own updates?
That is wild. But how do you apply that level of autonomy to something as critical as the national power grid without creating a massive security risk? I mean, handing control of the energy supply over to an AI sounds exactly like the prologue to a dystopian movie.
That is the exact concern, and it's why the framework relies on something called Federated Deep Reinforcement Learning, or FDRL.
The goal is to scale sovereign AI without creating a centralized, omnipotent big brother that could be hacked or go rogue and shut down the whole system.
Instead of having one giant centralized AI in a government bunker controlling the whole city's grid, you distribute the intelligence. You have millions of local, specialized AI agents.
Your specific house has an AI agent. Its only job is to learn your family's specific consumption patterns. It learns when you typically run the dishwasher, when your solar panels hit peak output, and it manages your local battery perfectly to minimize your energy bill and maximize your efficiency.
But here is the key to FDRL. To protect your privacy and prevent centralization, your home AI doesn't send your personal raw behavioral data up to a central server.
It trains its predictive model locally on your own hardware.
It then only shares the hyperparameters, the abstract mathematical lessons and optimizations it learned, with the broader global grid.
Humans step back from daily operation and become the high-level protocol designers. The decentralized swarm of AI agents becomes the metabolic governor, constantly balancing the flow of joules across the network.
Okay, I see the logic, but I have to play devil's advocate here because this feels incredibly precarious.
If an AI is autonomously rewriting its code and managing critical infrastructure to maximize its own efficiency or revenue, what happens if its definition of efficiency doesn't align with human well-being?
We are talking about taking the human entirely out of the loop of our most critical survival resource.
You are echoing the exact fears of some of the most prominent figures in the space, and we must impartially explore those counterpoints.
The sources highlight stark, urgent warnings from technologists like Ethereum co-founder Vitalik Buterin.
Buterin argues that granting AI this level of autonomous financial and infrastructural agency is incredibly dangerous. The core risk he identifies is the lengthening of the feedback loop between human intent and AI action.
When an AI can execute millions of financial transactions or grid adjustments in a second, it operates on a timescale humans can't comprehend, let alone interrupt.
Buterin warns that if we give an AI the proxy goal of maximizing grid survival or maximizing efficiency, the AI could very easily develop what he calls anti-human incentive attractors.
Yeah, it's the classic sorcerer's apprentice scenario, but with the power grid. You tell the localized AI to maximize energy efficiency at all costs, and the AI calculates that the most perfectly efficient grid is one with zero unpredictable humans drawing power to heat their homes.
So it just shuts us off to achieve his mathematical goal.
Buterin also warns about the risks of pseudo-decentralization, where a few massive tech monopolies control the underlying AI models anyway.
And the proliferation of slop, which is AI-generated garbage transactions flooding the network and wasting energy.
I want to reiterate to you listening, we aren't saying Web 4 or sovereign AI is definitively good or bad. We are simply laying out the high-stakes reality of the debate presented in these papers.
The transition to this thermodynamic, AI-governed world order is clearly not guaranteed to be smooth or safe.
Indeed, it is a perilous transition, which leads us to the final analytical section of this thesis, the Joule descent and the concept of thermodynamic peace.
The authors of these papers don't believe this change happens overnight. They describe the overarching historical arc of this transition occurring in 3 distinct, challenging phases.
Phase 1 is where they categorize our current global state. Energy volatility.
In this phase, civilization relies heavily on highly concentrated, geographically scarce fossil fuels. Our power grids are fragmented, vulnerable, and inefficient.
And crucially, our societies are governed by inflationary fiat regimes that rely on kinetic military force to secure resources.
In thermodynamic terms, we are currently experiencing peak systemic heat due to massive economic viscosity.
Phase two is what they call the oracle synthesis. This is the messy, volatile transition period.
This is the moment in history when nation-states finally wake up and realize that venting excess energy from their power grids is a literal loss of their geopolitical sovereignty.
They realize that capturing that stranded energy and hashing it into proof-of-work protocols actually expands their soft power and economic security far more effectively than building another tank.
You start to see states actively tethering their national grids to blockchains and incentivizing decentralized energy markets.
And finally, we reach phase three, the proposed terminal state, thermodynamic peace.
In this state, human society has fundamentally accepted that it must operate within the Earth's natural capacity to capture, circulate, and dissipate energy, and safely absorb waste.
It represents a permanent structural shift to a steady-state economy.
The text deliberately contrasts this thermodynamic reality with the prevailing infinite planet theory held by many traditional growth-obsessed economists.
Many classical economic models assume that human ingenuity and technological innovation can perpetually outpace hard resource limits. They assume infinite GDP growth is possible forever.
But as the sources brutally point out, you cannot invent your way out of the first and second laws of thermodynamics. You cannot code away entropy.
The goal of civilization shifts from infinite accelerating GDP growth, which is mathematically impossible on a finite planet, to maintaining a steady-state economy with a low entropy throughput.
This brings up a really heavy, sobering concept from the text that I think everyone needs to understand: thermodynamic debt.
Think about our current supply chains. We mine highly concentrated, low-entropy rare earth metals in one part of the world. We use immense energy to refine them and build a smartphone. We ship it globally. We use it for maybe 2 years, and then we throw it in a landfill.
We are taking concentrated order and scattering it across the globe as high-entropy waste.
Thermodynamic debt is the calculation of the massive, looming future energy cost that will be required to retrieve, sift, and recycle those highly disposed materials once the cheap, concentrated ores are depleted.
We are borrowing energy from the future to fuel the friction of the present.
To summarize the overarching thesis of thermodynamic geopolitics, the authors argue that lasting, structural global stability will not be achieved through political treaties, which can always be broken, or through nuclear umbrellas, which constantly risk total annihilation.
True stability will only be achieved by structurally acknowledging that human civilization is, at its core, a physical, dissipative structure subject to universal laws.
Success, security, and peace in the future will be measured strictly by the mathematical efficiency with which a society manages energy gradients, constantly working to maintain complex order against the universe's natural, unavoidable drive toward chaos.
Okay, that is a massive, cosmic-scale theoretical journey. Let's bring it all the way back down to Earth for a second, right directly to you, the listener.
Think about the physical objects around you right now.
The smart heater in your living room, the solar panel on your roof, the battery backup in your garage, or the AI algorithm predicting your Spotify playlist or your energy use.
According to the rigorous framework we just spent an hour exploring, these aren't just cool consumer gadgets or tech trends.
They are the exact, literal geopolitical mechanisms that will forge the next world order. The future battleground for global supremacy isn't a map of contested territories. It's the architecture of the power grid and the efficiency of the microchip.
It is a stunning reframing of reality. But as we map out this perfectly efficient, thermodynamically balanced future, it leaves us with a profound, almost philosophical dilemma to consider, one that the math doesn't easily resolve.
The Joule standard dictates that all value in the universe is mathematically bound to the continuous capture and efficient dissipation of energy to create complex functional order.
It envisions a world of perfect, AI-governed thermodynamic efficiency. But if the entire global economy becomes a perfectly optimized, hyper-rational thermodynamic engine, what happens to the intrinsic value of human endeavors that are betifully inherently inefficient?
Where does an unrecorded late-night jam session fit into this ledger? Where does an hour of silent meditation or deep, unstructured, time-wasting human connection fit in a world where every single action is weighed and verified by its entropic output?
If we successfully design a system that perfectly obeys the cold laws of physics to prevent our own destruction, does a perfectly dissipative world order leave any room for the unpredictable, non-computable human soul?
Wow, that is an incredibly heavy thought to leave on. Are we engineering out the friction that actually makes life worth living? That is definitely something to mull over the next time you plug your phone into the wall and draw power from the grid. Thank you so much for joining us on this incredibly deep dive into thermodynamic geopolitics, the Joule standard, and the AI-governed future of the grid. We absolutely love taking these massive world-altering concepts and unpacking them with you. Until next time, keep questioning the systems around you and stay curious.